Okay, have you ever actually stopped to wonder how a glass thread, one that is physically thinner than a single human hair, can transmit the entire world's digital information across continents? I mean, it sounds like absolute magic, right? But it's entirely based on brilliant, highly precise physics. Welcome to today's Explainer. I am incredibly excited to unpack this topic with you. We're going to take a structural journey straight from the abstract physics of light all the way up to the massive global applications that rely on it every single second. Here is our roadmap for today. We'll start with guiding light through glass, move on to the math of capturing light, check out the different types of fibers, look at why light signals lose power, and wrap it all up with the fiber optic revolution. Let's get right into it. So let's establish a quick baseline. An optical fiber is basically a super flexible, transparent strand of silica glass or plastic. But if you look at a practical real-world fiber, it's actually made of three main physical layers. The innermost part, the actual highway where the light travels, is the core. That's usually around 50 micrometers in diameter, which is literally about half the width of a human hair. Crazy, right? Wrapping around that is the cladding at about 125 micrometers. And finally, the whole thing is wrapped in a protective sheath around 250 micrometers thick, just to guard against moisture, physical pressure, and temperature changes.
Section 1. Guiding light through glass. This is the core principle of fiber optics.
The absolute secret sauce behind this technology is a phenomenon called total internal reflection. Think of it like invisible guardrails, keeping the light trapped from escaping. When a light ray hits the boundary between the core and the cladding at just the right angle, instead of bending or passing through into the cladding, it bounces completely back inside the core. Now, this illustrates the exact conditions needed for this little physics miracle to happen. It's a very precise combination of material density and launch angle. Step 1. The light has to move from a denser medium, our glass core, toward a rarer medium, which is the cladding. Step 2. The angle of incidence, basically the angle the light hits that boundary, has to be greater than what physicists call the critical angle. And step 3, boom, the ray reflects entirely back into the denser medium. Moving right along to section 2, the math of capturing light. We're looking at angles and apertures. So, to get light to bounce perfectly inside the fiber, you actually have to inject it perfectly from the start. Light has to enter within this specific 3D region called the acceptance cone. If the angle is too steep and falls outside of this cone, the light won't undergo total internal reflection. Actually, it just bleeds right out into the cladding and is completely lost. Which brings us to numerical aperture, or NA. Now, the crucial point here is that NA isn't just some intimidating math formula. It's the definitive measure of exactly how much light a cable can swallow up and transport. Because it's derived directly from that acceptance angle we just talked about, numerical aperture depends entirely on the specific refractive indices of the core and the clouding. Simply put, a higher numerical aperture means a greater light gathering ability, and that ultimately dictates how much data your cable can actually push through to your devices.
All right, Section 3. Different types of fibers. Single versus multimode cables.
Here we're comparing the two major categories of optical fibers. On one hand, you have single-mode fiber. This guy has a very fine, incredibly thin core that forces light to propagate in only one specific direction. Then, on the other hand, you have multi-mode fiber. This one uses a much wider core, around 100 micrometers, and because it's a wider lane, it allows light to travel in multiple different paths, or modes, simultaneously. Now, multi-mode fibers actually come in two distinct flavors. First, you have the step index fiber, which has a uniform core. That means the refractive index stays exactly the same until it abruptly hits the cladding. This makes the light travel in a really harsh zigzag fashion. But then you have the graded index fiber, which is honestly far cleverer. Its refractive index is highest right in the center and then gradually decreases outward. This brilliant design bends the light continuously, making it travel in a smooth, curved, helical fashion. And that greatly reduces signal distortion, or what we call modal dispersion. Take a look at this. Notice those jagged, sharp bounces of the step index design on the left and compare that to the distinct, discrete paths that light takes in general multi-mode propagation on the right. These different modes, basically high-order versus low-order paths, create completely different wave interference patterns inside the cable.
On to Section 4. Why light signals lose power. Let's talk about understanding attenuation.
So, if you're building a cable across, say, the entire Atlantic Ocean, you're going to have to fight three main culprits that cause signal loss. First up is absorption. This is where the inherent crystal structure of the glass itself, or tiny impurities, literally absorb specific wavelengths of light and turn them into heat. Second is scattering. This happens when microscopic variations in the glass density act like tiny roadblocks, completely disrupting the light's path. And third, bending losses. These occur when either macroscopic or microscopic bends happen during the cable's manufacturing or installation, basically forcing the light to leak out.
Because of all this, engineers have to use very specific, longer wavelengths to minimize data loss from something called Rayleigh scattering. Because this scattering is proportional to the inverse fourth power of the wavelength, lower wavelengths scatter incredibly fast. Fun fact, this exact same scattering is actually the reason our sky looks blue. So this physical limitation dictates exactly which bands of infrared light we can effectively use to communicate.
Finally, Section 5, the fiber optic revolution, from medical scopes all the way to global telecom. The payoff of replacing old-school copper wires is, well, it's massive. First off, the bandwidth is near limitless, operating in the trillions of hertz. Trillions! They're also much smaller and lighter, which makes handling and installing them way easier. Plus, because they carry light and not electricity, you get total electrical isolation. That means absolutely zero risk of sparks, short circuits, or electrical fires. And finally, they offer insanely high signal security. It is fundamentally almost impossible to decode or wiretap the light waves trapped inside that core.
And you know, this tech isn't just buried under the ocean for your internet connection, it has completely revolutionized countless other fields. It's used for two-way interactive TV services. In medicine, a bundle of multi-mode fibers acts as an endoscope to illuminate inside the human body, while lasers guided by these fibers can literally reattach detached retinas. In the military, using fiber optics in aircraft and ships strips away weight while maintaining strict communication silence. They even serve as complex sensors on guided missiles.
Which brings us to the end of our deep dive today. So next time you're streaming a high-definition video on your phone, or maybe you see a medical laser in action, I want you to ask yourself, how many billions of microscopic light bounces, perfectly governed by geometry and glass, made that exact moment possible? It's pretty mind-blowing when you think about it. Keep questioning the invisible technology running our world, and thanks so much for joining me on this explainer.